Okay, so in this chapter, this is chapter 13 out of Bruce's book, we're looking at alpha carbon chemistry. So just as a reminder, when you have a carbonyl or any functional group really, but a carbonyl in particular for this chapter, that this is the functional group, and these are alpha carbons. They're the carbons adjacent to the functional group, so these are alpha. And remember, for alcohols, the carbon isn't part of the functional group, so this is the alpha and this is the beta. Okay, so just to keep that in mind, we're talking about alpha carbons, and the hydrogens in particular on alpha carbons are known to be acidic. So if you think about, let's do acetone. This will be a simple example. Acetone is this guy. And I have a CH2 and an H. That's a CH3, right? And then this is CH3 on this side. Let me zoom in a little bit here. If a base comes along, the base can grab that hydrogen and the electrons have to go back to the carbon. So this is acid-base chemistry, and so you end up with CH3 from the acetone like this, and then you're going to end up with CH2 with a pair of electrons on it. Now, that'll have a negative charge, and this structure, this carbonyl lone pair structure is stable because it's the allylic lone pair pattern for resonance. We talked about that before. There's a resonance structure that delocalizes that charge onto the oxygen. So you'll end up with something that looks like this. So I'll put all the electrons there. That, and then a double bond between the C and the H2 like that. So these are resonance structures of each other, and because the resonance structures exist, it's easy to pull this hydrogen off because resonance, as you remember from earlier chapters, resonance stabilizes the anion, and it allows the structure to be more acidic, that is this structure. It allows acetone to be more acidic than it would normally be without resonance. Now, how acidic are these, right? So a table from your book, just to give you a reference point, for a alpha hydrogen, for example, on this aldehyde, the pKa is around 17. If it's in acetone, this pKa is around 20. Now, putting it in perspective, water is about 15. So these are not as acidic as water when you have a single carbonyl group. And then for a structure like this ester, it's 25. Now, the reason for the difference, especially on this one, it's easy to understand, is because this pair of electrons on the oxygen will compete with the pair of electrons on the carbon that's over here. Okay, so there's competition for resonance because of this oxygen has a pair of electrons on it, and that competition makes it so that you can't delocalize the negative charge on the alpha carbon as well. Okay, so that being said, acetone is not as acidic as the aldehyde, ethanal that's down here, and that's because if you remember, these CH3 groups are electron donating groups, and so what that does is it makes the anion, this anion in particular, it makes that anion less stable. The result is the aldehyde without the electron donating group. So that's electron donating. Let's just use the abbreviation E, D, and G. Okay. Electron donating group. Without the electron donating group in the aldehyde, the negative charge on the carbon can be stabilized a lot more efficiently. Okay. Now, notice what happens if you have two carbonyl groups on, let me get my small pen again, 2 carbonyl groups, alpha, right? There's one here and one here. So this guy is alpha to both of them, right? You notice the pKa is 10.7. So because the pair of electrons that's left after the hydrogen is removed can delocalize 2 different ways, it makes it more stable. So it has 2 resonance structures instead of the 1. And you see that same trend all the way down to here, where you have aldehyde and a ketone, then the pKa is all the way down to 5.9. So remember, these ones here are not as strong as water even as an acid, but these are actually stronger. And 5.9 is approaching the same strength. It's similar in strength to carboxylic acids, which are usually from 4 to 5 in that range. So with that in mind, let's look at a problem. I'm trying to use some of the examples because this is late in the semester where I use examples in the textbook. So what we want to do is identify the most acidic carbon in each structure. And really what that means is identify the most acidic hydrogens in each structure. Because carbons themselves aren't acidic, it's the hydrogens on them. But having said that, in order to do this, really what you have to do is you have to identify alpha hydrogens. So you need the alpha carbons, right? So we're looking for alpha carbons. And then if we look at the carbonyl functional group, there's 1 alpha carbon here. Now the other question is, are there any other acidic hydrogens on this structure? And the answer is no. There's no, like triple bonds, there's no carboxylic acids or things like that. So the most acidic hydrogen in this structure is the hydrogen that's here that's not drawn, right? So you have to be a little bit careful when you do these. Now on the other problem, we're looking for the most acidic carbon, or the hydrogen that's the most acidic in this structure. So again, we identify the alpha carbon, that's this one again, and then there's a hydrogen that comes off of here, like that. And then you have to look at this hydrogen versus this carboxylic acid. So based on information that we have up here, you know that esters, the alpha hydrogen is less acidic, right? So we know that this pKa is going to be fairly high. It's going to be higher than 25 at least, which is what it is right there. So that should be greater than 25. And then this is the other thing you have to look at. That's the carboxylic acid. That pKa is around 4 to 5. So that's the most acidic carbon in that structure. And so now we come to another topic which is important in this chapter, and that is the idea of tautomers. So a tautomer is a name that we give when 2 constitutional isomers are in equilibrium with each other, and ketones are in equilibrium, or carbonyls are in equilibrium with their enol form. So let's look to see what that really means. Okay, so again, I'm going to just deal with acetone. So I have like this, right? CH2 and then an H. That's acetone, and this is CH3. There's an equilibrium, so an equilibrium arrow, not resonance, it's different, between that structure and this structure. So you can see that these are not resonant structures, because what happens is this hydrogen that's here and the enol ends up on the oxygen. And if you remember, in equilibrium structures, you can't have atoms moving. Or in resonance structures, you can't have atoms moving. But that's part of what makes tautomers different than resonance structures. So part of the question is going to be in a second, how do we know what those structures are? And the other one is how do they interconvert? And so I want to point out one more thing. This is a keto form. This is the enol form. Now, if you have the anion for the keto form, that is, you have this. So a base has reacted with it, and you end up with HCH2 here like this. And the lone pair in a negative charge. So from here to here, we had a base. And the base removed the hydrogen. This is known as also a keto form, because it has the ketone functional group in it. But on the other end, we end up with this. And this is known as the enolate form. If you remember, when you hear the term ATE at the end, that implies that it's an anion. So then we'll end up with, that's not it's a carbon. So this is known as the enolate. And really, the only difference is whether or not it happens in the presence of a base or not. If this reaction actually happens in the presence of acids or bases, but if you have a base, you usually end up with what we call the enolate ion. So how do you identify the keto and the enol forms? It's pretty simple, actually. If you look at a ketone like this, and I'll just draw a random one here, or let's do an aldehyde, right? This is the alpha hydrogen. You can't see it, but I'm drawing. But that's where the alpha hydrogens are. That's the alpha carbon. The enol is, all you need to do is make the double bond between the alpha carbon and the carbonyl, and then put the hydrogen onto the oxygen like that. Okay. Now, you might have recognized that you can occasionally have a couple of different enols for every ketone, and I'll show you that in an example. But here's an example of a problem. Draw the enol tautomer for, and this is cyclohexanone, and to do the enol tautomer, what you need to do is identify both alphas there, because in this case we have two. When I did the aldehyde, there was only one alpha hydrogen. And when I identify the alpha hydrogens, you can imagine what the enol looks like, because between that alpha hydrogen and where the oxygen is, you'll have a double bond, and the oxygen will now have an extra hydrogen. Remember, here there's two hydrogens. Here there's only one. So one of those two hydrogens went to go reside on the oxygen. So this is the keto, and this is the enol. Now, having said that, there's another enol in that you could have drawn, but structurally it's the same. That is, it's just the mirror image of the other. So those are actually both the equivalent. These are the same. But if it's asymmetric, so let me give you an example of an asymmetric ketone. Like this, right? Then you could have two different enols. One would be this. One to the oxygen. And the other one would be with the double bond on the other side. Like that. And those aren't the same, because the position of the methyl group were relative to the double bonded carbons. So you actually could have two different enols. Now your book goes into a little detail about the distinction between these two, but I decided to leave that off. It's important to know how these form and what they look like, but I think for what most people are going to be using this class for, you'll either learn the differences between the two enols later, or you won't need it, and you won't have it in the class. So in any later classes. But if you take the more advanced organic chemistry, definitely that is something that we cover. So what I'm going to do real quickly is show you how these two reactions are catalyzed by both acid and base. So let's talk a little bit about why this reaction is slow in the first place. So if you have a ketone and you want to go to the enolate form, so I'm not going to draw the carbon anymore. I'm just going to draw the hydrogen on there. This hydrogen's got to move over to that oxygen, and then you have to build up a negative charge. So you have to build a carbanion here. And it turns out anytime that you separate two charges, that's going to take some energy. So if you do this reaction and try to do it without a catalyst, what you'll end up having to do is pull that hydrogen off. That'll leave a negative charge behind, and you'll have an H+. That takes energy. So as it turns out, that's slow because of the requirement of energy. The way that this is done with an acid catalyst is the following. So I have a hydrogen ion, so that's the acid, and you first protonate that oxygen of the carbonyl, and that gives you this. Now, you haven't had to separate the charge, and all you had to do was to protonate the oxygen, and so that's a relatively easy step to do because you're adding an acid to do that. The second step is in this particular example is water is usually present, but it doesn't have to be water. The water grabs this, and we get that. And you haven't had to separate any charges. You had a positive charge up here after it got picked up, and so you end up getting, let me draw the arrow down here actually. You end up getting your enol. Keep wanting to draw a double bond on that oxygen, huh? And so you hadn't had to separate any charge. You added an acid so that wouldn't have to be done. And then that makes this reaction faster. It lowers the activation energy for the reaction. Similarly, this reaction can be catalyzed using a base. So in the base catalyzed reaction, you have your ketone, or your aldehyde, your carbonyl, and then you bring in a base. And again, remember, a catalyst's role is to make a reaction faster, and it will convert this into the enol, or the enolate, which looks like this. Oops, sorry. Like that. What you have left after that process is H2O. And then this can pick up the hydrogen from a water, and that leaves you with, I'll draw it over here, the enol again. Like that. So the purpose of the catalyst is to make these reactions faster. And so almost always when you see these kinds of alpha carbon chemistry, there's almost always some sort of catalyst involved in the reaction in order to make the reaction go faster. Sometimes we use acid, and there's specific instances, and I'll show you one later. But primarily, and for the most part I should say, we use bases to make these reactions happen. So here's an example of where you could use an acid or a base to make a chemical reaction take place. So the first reaction we're looking at is called a halogenation reaction. And in a halogenation reaction, the carbon, the alpha carbon, oops, sorry, wrong pen. The alpha carbon is going to be a nucleophilic carbon. And what it's going to do is it's going to attack the bromine and add the bromine to this carbon. Okay, so what happens is it looks like this. You're going to end up with this as your product. And the other part would be what's left for the other bromine would be a bromide ion. So this is how this happens. First of all, let's say it's under basic conditions, right? The way that we would draw this out is we would first form the enolate. Now, if you need to review again, because I've been taking pauses myself here, the enolate is formed in this step of the reaction using this same mechanism. Okay, so I can grab the enolate and form this guy here. Okay, the hydrogen and form that guy there. Okay, so having said that, this is going to form. And so this is a nucleophilic carbon. Now bromine can be an electrophile. And that nucleophilic reaction goes like this. And so that's what gives us this product. Now, it could also happen under acidic conditions. I'm not going to talk about all the different instances, but I just want you to get the idea of the kinds of things that can happen. And the reason they're happening is this carbon is nucleophilic. The alpha carbon is a nucleophilic carbon. And basically, if you're looking at the product, right, I've done a substitution of a halogen for a hydrogen. So let's look at this alkylation reaction. This is another kind of reaction you can do. Again, typically can be done under basic conditions. We can form the enolate. Now, which will look like this. And maybe I should make something clear too. It just occurs to me. The way that I'm getting to this structure is, you'll notice that in the above example, and I'll go back to that in a second, what I drew actually was this. So this is the enolate. If you look up here, that's what I drew up here. This is my enolate. Okay, and then I went to the enol form, but from the enolate form, I have resonance structures. This is just the resonance structure of the enolate. Okay, so when we think about it acting as a nucleophile, we really think about the carbon, the CH2 group, is the nucleophilic carbon. And then CH3Br, methyl bromide, this is an SN2 reaction, right? And the alkyl halide, the substrate, is my electrophile, and then the alpha carbon is my nucleophilic carbon, and so the product of my reaction will look like this. And then I'll have created another Br minus like that. But what I've done essentially is I've added a carbon by using an alkyl halide in an enolate reaction. So I thought it might be important to summarize a couple of ideas from this first section. One, alpha carbons are acidic. And really what we mean by that when we say it is we mean the hydrogens are acidic that are attached to alpha carbons, but we generally just say alpha carbons are acidic. Part of what that leads to is we have enolates, enols, and enolate ions. An enolate is an ion, right? Can be formed with the help of acids or bases. Okay, and the third thing that's important to recognize is that enols or enolates, the alpha carbon, is nucleophilic. So there are different kinds of substitution reactions that can take place at that alpha carbon, and we looked at two examples. We looked at halogenation, and another one that we looked at is alkylation. Now, in recognizing, and I should maybe done this one earlier, in recognizing the enolates or the enols that can form, you have to look at alpha hydrogens. So this is an alpha carbon, so there's hydrogens. So each one of these can form an enolate, and the enolate occurs, or the enol occurs between the alpha and the carbonyl carbon. Like that. So those are the two options. And so if you have an asymmetric carbonyl, then you can form an enol on either side that's different. So now we have an interesting situation. The alpha carbon, and I'm going to use this one on the right to represent the alpha carbon here, this guy. The alpha carbon is a nucleophile, but this carbon, and we talked about this in the earlier chapter, this is electrophilic. So it turns out, and remember, the reason it's electrophilic is it has a very large partial positive charge because of the oxygen and the double bond from the oxygen. And so we have a situation where we have a nucleophile and an electrophile on the same molecule. You'll notice that this molecule and that one other molecule are the same molecules. I just chose to draw the hydrogen out. So it turns out that an aldehyde, or a ketone, can act as both the electrophile and the nucleophile in the same reaction. So how does this work, right? So if I were to draw the nucleophilic form on the right-hand side, I would take and I would do this. Remove the hydrogen, acid-base reaction. I don't think I need to go into all the details there, but remove the hydrogen in an acid-base reaction, and then I have this. So there's a negative charge, and then I can have an addition reaction take place. And now what I'm left with, let me do a little erasing here. This pair of electrons can go up. I'm going to end up with this. CH3. In fact, let me do this. This usually helps. 1, 2, 3, 4. So I have CH3. And then on the carbon that I called number 2, I'll have an O minus. I'll have an H. and then I'll have a CH2, and I'll do this as well. I'll draw this in a different color. Then C double bond, and then H like that. Now, this can pick up a proton in solution. These are usually aqueous reactions or in an alcohol, so that's where the hydrogens will come from. And I'll end up with this as my product. And I'm going to rearrange it a little bit so it's a little neater. I'm going to switch the position of the hydrogen. And then I have this. Now, this product is known as an aldol product. This is the aldehyde, and this is the alcohol. So putting those two words together, we have aldol, and this is known as an aldol reaction. And you'll notice a couple of things about the aldol reaction that happened. Let me get a highlighter here real quick. Yeah. In the reaction, one of the carbons is the nucleophile, and then the carbonyl is the electrophile. So one of the alpha carbons is the nucleophile. One of the carbonyls is the electrophile. In the process of doing this, I doubled the number of carbons. So I went from 2 carbons in each to having 4 carbons in the product. And then one of the carbonyls, the nucleophile side, this carbonyl is unchanged, where the other one becomes an alcohol. So we call this an aldol reaction. It's a very common reaction, and one of the reasons why we're doing this particular section is this has a lot of ties to biology and biochemistry, and I think it's important for you, if you're going to take this elementary organic chemistry class, is to learn some of these connections, because that's the reason why you're taking this class for most people. Okay. Now, there's also something called an Aldol condensation reaction, which I'll follow up with in a second. But what I thought I'd do is do another example of an aldol reaction, and this time using propanol. And we'll go through the practice of how I recommend you write these out so that you don't make any mistakes in determining what the actual product is. Okay. So propanol, we need to write its structure first. So CH, just 3 carbons, right? So CH3, CH2, and then C double bond, and then H, because it's an aldehyde. And then I'm going to have another one. And this is there's a couple of ways that you could do this. One is to do this actually. I'm going to draw, now that I've drawn the electrophile, I'm going to draw it so that the alpha carbon is next to the electrophile. So this is my nucleophile. So here's my alpha, and this is what I'll know is going to happen. One of these hydrogens will go away. One of those will go away. But this, let me get a different color pen, is going to attack here, like that. So what I'm going to do is I'm going to number the carbons so I know exactly what's at each position. And being a little bit more systematic about it now, I'll start with my nucleophilic carbon side, and I will draw 1, 2, this will be 3, 4, and 5. So I'll have a 5 carbon chain, and the easiest thing to do is to actually draw that first. So the product for this will have a 5 carbon parent chain, and then off of the second carbon of a CH3 group. On the third carbon, I'll have an OH, and then it'll be followed by an ethyl group, or CH2, and a CH3. So the next thing I'll do is we'll work on drawing that out correct. Oops, knocked my mouse over there. So I'll start with the C double bond O and the H. This is number 1. And then I'll have a C, which will be a CH, and then a CH3 that comes off of it. And then, so this is 1, 2, and this will be number 3, so I'll have C, and then I'll have OH, and then I'll have CH2 and CH3. So that's 2, 3, 4, 5. And then I just have to fill in the hydrogens that are missing. I'm missing a hydrogen here, and I think that's it. So again, this is how you do the aldol product. Now, I also want to show you this in line drawing form, because when you do line drawings, it's far easier than doing like what we're doing with this sort of condensed Lewis structure. So I'm going to show you the same example, but I'm going to use a line drawing. So I'll draw propanol, and actually I'll draw it like this. And then I'll draw it like this. So there's 2 of them. And then what I'm going to do is I'm going to have this one be my nucleophile and this one be my electrophile. So that means when I attach these two, again, the alpha carbon to the carbonyl. So now I can number this. I can go 1, 2, 3, 4, 5. So now what I need is a 5 carbon chain. So I'm just going to draw that. And so I'll get my blue pen back out and go 1, 2, 3, 4, 5. So that's my 5. 1, 2, 3, 4, 5, like that. On carbon 1, I'll have a double bond like this, and there's a hydrogen, so I'll go ahead and draw that. Now on carbon number 2, again, let me number these. This is 1, 2, 3, 4, and 5, like that. So on carbon 1, I had the carbonyl. On carbon 2, I had a CH3. On carbon 3, I have the alcohol, like this. And then that's my aldol products. And because it's a line drawing, you don't have to figure out where the hydrogens are that you didn't draw, because you don't draw them anyways. So this is the same. These two structures are equivalent to each other, but you can see how much cleaner and more efficient the line drawing is when you do it that way. Again, a couple of things to note. I've doubled the number of carbons, right? But not all of them are in the parent chain. I have 1 carbon that's down here. So I started with 3 and I ended with 6. I had the 2 carbonyls to start with, but the nucleophile remains a carbonyl. So this is from the nucleophile side, and the electrophile becomes an alcohol. Okay, so let's look at our next reaction, which is called the Aldol Condensation reaction. And really the Aldol Condensation reaction is just a continuation of the aldol reaction. Now these reactions are typically done under basic conditions. So I have sodium hydroxide, and the sodium hydroxide grabs the hydrogen and it releases the hydroxide. So this is a catalytic reaction. The OH helps to facilitate this reaction, and so I end up with a double bond. This is a beta elimination, because this hydrogen, this is the alpha for the alcohol, this is beta for the alcohol. For the carbonyl, it's alpha, but it's still a beta elimination. And you'll end up with CH, oh sorry, I already started it. CH3, CH2, and then C double bond, H. I guess the H is on the bottom. I'll just draw it on the bottom. And then I have C, and then CH3, and then C double bond O and H. So that's that product. So this is called an aldol condensation. What's the thing that was eliminated? Essentially, you got rid of an H2O. So the other part of this product is an H2O that gets eliminated because I have an H and an OH, right? That gets pulled off. So when we say condensation, typically we think it means like water is removed, and that's okay in this case because water is removed. But in organic chemistry, condensation has a broader definition. It's just the removal of a small molecule of material from another larger molecule. So by pulling the water out, that's the smaller molecule out of this larger product. Oh, I'll use that as a pointer. It just occurs to me that makes a decent pointer. Okay, so let's see here. The next type of reaction to talk about is very similar to the one we just looked at. It's called the Claisen condensation. So in a Claisen condensation, I have a carbonyl functional group. Now you'll notice again that these two molecules that I've drawn are the same. So one is going to be the nucleophile, and the one I've drawn the hydrogen out on, that's this one here. This one will be my nucleophile. And then the other one, that's this one over here, that'll be my electrophile. So I have my alpha carbon, that's the nucleophile, and my carbonyl, that's the electrophile. So in this particular reaction, what will happen is a base is used, and I'll talk about the base here in a little bit. It'll come and remove, it's a negatively charged base actually, we'll remove that hydrogen and put the electrons onto that carbon. So now what I have is I have this enolate resonance structure. Remember the resonance structure. So I have this CH2 negative and then C double bond O and then OCH3 like that. So this is my nucleophile, and it's going to attack my electrophile like that. What that's going to leave me with is something that's a little bit different than when we were doing the aldol reaction. I'm going to have an O minus here. I have an OCH3 here. And then I'll have my CH2 that I just added, so I'll do that one. I probably should have switched to colors, but I'll do that in blue as a CH2, then C double bond O, and then OCH3. So that's what I have right now. But what happens is, unlike the aldol reaction, this is a leaving group. Okay, so going back up here, all right, what was there instead of an OCH3? We had a hydrogen, and the hydrogen is a very poor leaving group. So it doesn't leave. That's why we get an addition reaction. In this case, what happens is I have a substitution reaction. So this is going to go like that, and those electrons will dump off to the oxygen, and what that'll leave me with is this, CH3, C double bond O, CH2, and then C double bond O, OCH3 plus OCH3 minus. Okay, now hang on, let me just highlight this a little bit. Let's use this here. This is from here. Okay, and then the other one, that's this guy. He's still all there except for the one hydrogen. And what's happened is the group that's in yellow, that is this group here, is actually substituted for this OCH3 here. This product is a type of compound that's known as a beta keto ester. And again, these are very important reactions in biochemistry and in biology, so that's why I'm including them. They're very common, and I'll show you some examples here in just a little bit. But this is a product of the Claisen condensation reaction. Now, Claisen is actually a scientist's name. Aldol is just aldehyde alcohol, but Claisen is actually somebody's name. Some of these reactions, there's one called the malonic ester synthesis and the Keto Ester acid ester synthesis, I think is the other one. And there's a bunch of these names. They're named after compounds, but this one happens to be named after a very famous chemist from the early, I think, 1700s named Claisen. Anyways, the idea is essentially this reaction is the same as the aldol reaction, except I have a leaving group. And because I have a leaving group, instead of being an addition reaction, it becomes a substitution reaction. Okay. It's called a beta keto ester because, remember, C double bond O is a keto group. And so this is alpha, beta, and then gamma and all that stuff. And this is the ester part. And these are very important compounds in biochemistry. Okay, so that's the beta keto ester that you form. And now let's talk a little bit. Let's do one example. I want you guys to sort of pause the video and draw both the reactant out 2 times and then decide what the structure of the product's going to look like. And so you can go through all the steps that I talked about, number the parent chain of the product compound, and then knowing that this is a Claisen condensation reaction, draw the known functional groups at the different substituent positions. So let's walk through it. Hopefully you got 2 structures drawn like this. This is my nucleophilic, this is my alpha nucleophile, right? So this is the nucleophilic and this is the electrophilic side. So the electrophilic side is going to get attached here. Now this is a substitution reaction, so I have this group that's going to leave, and I can draw out what I believe the parent chain will look like. So let me number again what I think it'll look like. I'm going to start with a 1 here, 2, and then it's going to jump all the way over to here, 3 like that, 4, 5, and 6. And so I'll draw that out, and I like drawing it as a line drawing. I've said that already once. But that's what I'll be doing like this. It's a 6-carbon parent chain. So 1, 2, 3, 4, 5, 6. I know at carb, so this is, let me draw the numbers in. This is 1, 2, 3, 4, 5, and 6. Let me draw what the groups are at each position. So at carbon number 1, I had an ester. So OCH3 like that. Carbon number 2, I don't have anything, or do I? Right? Look at that. What's that carbon number 2? Well, carbon number 2, I'm going to connect to carbon number 3. Of course, that is, I'm going to go from here to here, or here to here, like that. But then on carbon number 2, you'll notice I have another group hanging off the side. That's that guy there. Okay, so now what I need to do then is draw that group in. And that'll look like this. CH2, CH3. So it's an ethyl group. Now on carbon number 3, I'll have my carbonyl back. And that's what makes this different from an aldol reaction. It's a substitution and not an addition type reaction. And then carbons 4, 5, and 6 are just a straight chain. So this is my Claisen condensation product. Now if you wanted to, you could have also drawn it out by just writing this and then drawing the CH2 and then connecting it to a carbonyl and then drawing it all out. But I think this is just a lot easier to do and to look at. One more important kind of reaction comes from a compound closely related to this beta keto esters, and that is beta keto carboxylic acid can be decarboxylated. That's the reaction. In biology, we see decarboxylation and carboxylation happening all the time. So I'm going to show you how we know this reaction happens in chemistry. So to start with, we take a beta keto ester. Well, that's what we have here. This is a product of an aldol reaction. That's this guy here. Okay? Oh, I could use my green pointer. That's my beta keto ester. and I treat it in water and sodium hydroxide, and that removes the OCH3 group. Oh, you know what? I forgot to mention something. We'll go back up to here for a second. Sorry. You notice that the base they used for this was CH3O-, which is the same as that. The reason that's done is because if you had used hydroxide in this reaction, you would have ended up with an OH here because it will substitute for the OCH3. And so it's important to recognize that the base is actually whatever the ester group is, whatever this group is here, that's what you usually use as your base. Okay? Okay, let's go back to the decarboxylation reaction. So this is a beta keto ester as a result of a Claisen condensation reaction. And then we had sodium hydroxide and water, and we end up with a beta keto carboxylate or carboxylic acid. Now it turns out this, if you heat it, can be made to release carbon dioxide. So I wrote a minus CO2 down here, so I just redrew it down here. And I'm going to show you the arrows that are necessary for this to work, and it's a lot easier than you might think. These electrons go here. These electrons go here. And so what you end up with is this. Plus, and the other part is this. Well, I guess if I were drawing it the way it was on the screen, it would be O like this and O like that. But that's carbon dioxide, it's CO2. It's a linear molecule, so most people will draw it like that. Okay? Now, one of the reasons that this happens is when you heat this up, gases can be liberated, and that helps, using Le Chatelier's principle, helps to make this reaction go towards the product side. So decarboxylation can very easily be done, right, if you have a beta keto carboxylic acid, because this is an enolate, and right, it's in resonance with this, and the resonance gives it stability. Now, what eventually happens, and again, the negative charge likes being on the oxygen because the oxygen is more electronegative, but we won't talk about that too much more. That's the resonance structure. But eventually what happens is you'll pick up a hydrogen, let's say from a solvent like an H2O, and then you'll end up with the keto form of the original enolate. In this case, you'll be getting acetone back like this. Okay? So that's a very important reaction. You can both do carboxylation and decarboxylation. The requirement for this to work is that lone pair of electrons has to be stabilized somehow. And typically for these reactions, it's stabilized by resonance. So there's a question in your book. It says, which compound will decarboxylate when heated and why? All right. Well, this A, you can see, will decarboxylate. In fact, it's the same molecule that's up here. It can decarboxylate because I have a carbonyl group, and I have a carboxylate or carboxylic acid, and that can be pulled off as carbon dioxide. The negative charge that is created here can be stabilized by resonance with this oxygen here. So looking at compound B, right, can you do decarboxylation here? Well, part of the thing that you need to make decarboxylation to work is you need to have carbon dioxide that's formed that helps to complete this reaction, drive the reaction forward as a gas is formed. And because there's not a second oxygen here, that is, there's nothing on this carbon, it's a carbon, I should say, it's not an oxygen, then you can't make the decarboxylation work because you can't force the CO2 off. Now, an equally important example to sort of understand would be something like this. So now I have a carboxylic acid, which can be decarboxylated uh, if it's stabilized when these electrons in this bond get pushed onto this carbon. Now, it can only happen, it can only be stabilized in these compounds if the electrons can delocalize to this carbonyl, but this is an sp3 carbon, and you can't delocalize electrons onto that carbon because it doesn't have the p orbital available for delocalization. Okay, so we have situations where we have a beta keto ester or beta keto carboxylic acid or carboxylate. Those can be decarboxylated. You need to be able to get CO2 off, and you need to be able to delocalize this charge that would build as these electrons, the ones highlighted in yellow, are pushed to that carbon. And since we have an sp3 carbon in the way, we can't have that delocalization taking place. So I wanted to show you a couple of places. Your book has some nice examples of where we see these kind of reactions, these alpha carbon chemistries in biology. And so I don't expect you to memorize these, but I'd expect you to sort of remember them later when you need them. I mean, when you're going to be taking your biochemistry classes, for example. So here we have an example of an aldol reaction in gluconeogenesis. Now, in gluconeogenesis, we take smaller carbon-containing compounds, derivatives of triglycerides, and convert them into fructose and then eventually into glucose. So this is how the body makes glucose from smaller molecules. And you'll notice that we have dihydroxyacetone phosphate and we have glyceraldehyde 3-phosphate. So these may be, if you've taken like a bio, I think it's a bio 11, 11A and B. These may be familiar to you because they're the compounds that are used in some of the metabolic and pathways that they're typically talked about. So these two molecules actually come together to form glucose. And you'll notice both of them are 3 carbons long. So I have 3 carbons and 3 carbons, and then fructose is 6 carbons and glucose is 6 carbons. And glucose and fructose are actually isomers of each other. Stereoisomers are, constitutional isomers of each other. But you'll notice that 3 carbons to 6 carbons, that's the pattern that we typically see in aldol reactions. And so what we have is we have a carbonyl functional group, and this is my nucleophile. So this is my nucleophilic alpha carbon, and that's going to attack my electrophile. And so here's my electrophilic carbon, that's right here. Okay. And so what happens is the attachment is going to be from this carbon to this carbon. So the new bond that's formed is actually this guy that's right here. And remember, in an aldol reaction, you have a carbonyl functional group and an alcohol that forms. So this is the product of that aldol reaction. So fructose 1,6-bisphosphate. Bis is the word we use so that we don't confuse it with di. It's the same. It means the same thing. So anyways, we have like adenosine diphosphate, triphosphate. So since those terms come up all the time, bis is another term that can be used to represent two. So fructose has 2 phosphate groups on it, not 2 phosphates on the same side. That allows us to, the aldol reaction allows us to form the basis of glucose, which will then get converted, to fructose and then to glucose eventually. Those are all enzymatic reactions. So another interesting application of alpha carbon chemistry is in fatty acid synthesis. And so in the body, I don't know if you're familiar with fatty acids, but fatty acids are often 12 to 22 carbons long, typically 16, 18, that kind of thing, carbons long. So they're very long carbon chains, and those are created in the body starting with acetate. And so we have acetate, and it reacts with coenzyme A and forms what we call acetyl-CoA, and that's probably something that's familiar to you from Bio 11 or A or B, I don't know which it is. Now, coenzyme A, just not to pass anything too far past you, is this, okay? So it contains a sulfur, it's a thiol, and that sulfur can form a bond with the carbon, and this is known as a Thio Ester because of the presence of a sulfur instead of an oxygen, and it utilizes the energy from ATP, adenosine triphosphate, and breaking a phosphate oxygen bond actually. It goes from ATP to AMP, adenosine monophosphate, and this is pyrophosphate. It's actually a diphosphate that comes off when that process takes place. And so that's how acetyl-CoA is made. That's an ester, and then a thioester, and then we carboxylate that. So this is the opposite of decarboxylation. We can add a CO2. This is the CO2 from carbonate or bicarbonate. And so we get malonyl-CoA from that. And then there's a transesterification process. So if you remember from earlier chapters, when you have an ester and you substitute it with a different group, that's known as a transesterification. Remember, esters are carboxylic acid derivatives with an O and an alkyl group instead of a hydrogen. So if this is R prime and then you switch it to OR double prime, that's a different R group, that's a transesterification reaction. So what actually happens is there's a thiol, which is part of a protein, which does a transesterification with the acetyl-CoA to form a different thioester. That's this guy here. Now, this is where the alpha carbon chemistry can start. So we take our malonyl-CoA, that's this guy here, and then our new 2-carbon thioester, and we get a beta-keto thioester. This is the product of a Claisen reaction. So basically what I've done is I've gone from 2 carbons now to 4 carbons. There's a series of reactions that takes place that you can see down here. There's a reduction to an alcohol, a dehydration, so a beta elimination. So now this looks a lot like a aldol condensation product actually, and then a reduction. These are all enzymatic processes. There's no mechanisms that we'll go over for those. And then once you have this 4-carbon thioester, that's this guy down here, it's repeating itself down here. Then you can take, again, this is the malonyl-CoA, sorry, that's this guy here. I don't know if I can get them all on. Let me squeeze it down like this. That's this guy up here. This whole process can repeat again. And once that process repeats, now you have a 6-carbon beta thioester, beta keto thioester, and then you can go to, after 6 you can go to 8, and then after 8 you can go to 10, and after 10 you can go to 12, etc., all the way up to 16 usually, and then that's when the process stops, and then there's modifications. But the deal is you're adding 2 carbons at a time. So if you're actually looking at fatty acid esters in nature, they all have an even number of carbons in them because they all essentially rely on this process for the initial production. So that's just kind of a overview. We'll be talking about carbohydrates and lipids and amino acids, and we'll see a few more examples maybe. But in those chapters, we'll be mostly talking about some of the chemistry involved with some basic reactions of carbohydrates, amino acids, and lipids, fatty acids, and things like that. So that covers it for this chapter. Again, if you have questions, feel free to contact me and let me know what your questions are.